Welcome to the 16th lecture in mechanics of materials. From this lecture on, we are going to look at how to solve different boundary value problems that is of engineering interest. Till now, we have seen about the 4 concepts in mechanics, namely force, displacement, stress and strain, and 4 equations that connect these concepts. Basically, the equilibrium equations, the strain displacement relationship, the compatibility conditions and the constitutive relations. We also saw what energy is and how to compute the strain energy per unit volume, your load potential and the total potential in the last lecture. Okay. From today's lecture on, we will try to apply these concepts to solve some boundary value problems that are of engineering interest. The first boundary value problem that we are going to look up is that of an axial member. Okay. The axial member is one wherein I have this member subjected to some axial force and one end is fixed. Okay. This is the axial member that we are interested in analyzing first. Let us go ahead. So, I have this member to which I am applying a force P. All of us know that once you apply a force P, it is like a uniaxial state of stress, uniaxial loading. So, we saw when you looked at uniaxial state of stress, we saw that the stress is given by this tensor P by A 0 0 0 0 0 0 0 0, and in the uniaxial loading case we understood that the strain would be, if this is A and B and if this displaces by amount delta B, this is delta B by L, where L is the length of this member. Okay. 0 0 0 and transverse displacement in y direction by the height of the member 0 0 0 transverse displacement along z divided by the breadth of this member. We saw this when we looked at the uniaxial loading case. Okay. To solve boundary value problems, what we are interested is in this relationship of the sigma xx stress to the strain epsilon xx, which was this, which was E times delta B by L. Okay. So, we want to relate delta B now using this relation, delta B is P L by E A. This is a takeaway equation that we will be using to solve different boundary value problems involving axial members. Okay. What we have used is, we have used the equilibrium equations to understand that the stress is given by P by A, okay, and then we have used the strain displacement relationship to write the strain as delta B by L, and here we have used the constitutive relation to write the stress as E times epsilon xx. In other words, what we have done is, we have used the equilibrium equation to relate the applied force to the stress, we have used the strain displacement relationship to relate the displacement to the strain, we have used the constitutive relationship to relate, we have used the constitutive relation to relate the stress to the strain. Okay. So, that is what we have done in this problem, and we have got the relationship that delta B is P L by AE or EA. Okay. Now, let us apply this to some problems that is of interest. The first problem that I am going to solve is the following. I have a stepped cylinder okay. This is of length 2L, this is of length L, it has 2A as the area and E is its Young's modulus, this member has E as the Young's modulus and A as the area. Okay. Let me assume as usual this to be Ex, Ey and this to be EZ, and let us assume that I am applying a force P along this rim, along that rim I am applying a force P. Okay. Let us also assume that this is A, B and C, and I am interested in finding what this displacement delta C is. Find the displacement of the section C, okay, for this loading. Okay. Now, how will you go about doing this? First I have to draw the free body diagram of AB. First step is to draw the free body diagram of the respective axial members. The two axial members are AB and BC. Since there is no force acting at C, there will not be any force acting at B either, whereas here there is a force P acting here, there is a force P acting there. So, what will happen is, if I were to remove this support, that support is going to prevent from A from displacing, and it will offer a reaction force P there. Okay. It is similar to the case wherein we saw just now AB subject to axial load P. Okay. So, this edge would displace by delta B, which is given by P 2 times L by E 2 times the area, because this has the Young's modulus C, 2A is the area of the cross section and length is 2L. Okay. In other words, delta B is PL by EA. Okay. Since there is no force at B, if I were to analyze the structure, BC, there is no force here, this point moves by delta B, and so this will move by delta C. Okay. Since this edge moves, this surface moves, this surface also will be moving by some amount delta C. In this case, since there is no force applied, delta C is going to be equal to delta B, which is PL by EA. On the other hand, if I had applied a force F at C and say, so instead of solving that problem, I was looking at this problem, say there is a force F applied here and there is a force P applied over there, then delta C A B C again, this is 2A E A E, this is 2L and this is L. Then for the free the free body diagram of BC would be something like this. F. So, this delta B, and if this displacement is delta C would be delta B plus, in this case it is a compressive force. So, minus F into the deformation caused by this force F, which will be again given by PL by AE. this member is of length BC is of length L, it has a cross sectional area of A and Young's modulus E. So, from our previous discussion that delta B is PL by EA for applied tensile load. Okay. Here I am applying a compressive load, so that is why it is negative, okay, minus F into L by AE. So, now delta C would be minus FL by AE. Okay. Now, delta B is not same as what we had before, because the force acting on member AB also will differ now. Okay. So, the force acting on member AB would be the following. There is a force P acting here and there will be a force F acting here. So, the net force from equilibrium is P minus F, right, because they are in opposite direction, the net force acting on member AB would be P minus F. So, delta B would be this force, this P minus F into L by AE. Okay. From our expression for the displacement at a point P to a member for which the applied axial force is a P which is in tension. Okay. So, this will be the displacement of B. So, now delta C becomes PL by AE minus 2F L by AE, substituting for delta B in there. Okay. Okay. So, that is the displacement of C, the point C. Okay. Now, let us assume that the C is not free to displace, but I have a boundary at a distance delta from C. Let us assume that C is not free to displace, but it is limited to displace only by a certain amount delta. That is, this is problem 3 that I am looking at. This has area 2A, E, A, E, and let us say this distance is delta and this length is as before 2L and this distance is L and this is A, B and C, and I am applying a force P at the rim of AB, at the intersection of the members AB and BC. Okay. In this rim I am applying a force P. Now, I want to find the member forces. Forces FAB and FBC. Okay. Now, there are various ways by which you can solve this problem. Clearly, there are two cases. The first case is before the gap closes and after the gap closes. The simplest way of solving this problem is the following procedure. Okay. Again, you draw the free body diagram assuming the gap is closed. Okay. First, you assume gap is closed and draw the free body diagram. Okay. So, for member AB, BC, if gap is closed, what does that mean? C there will be some reaction force coming here which is F, say there will be that reaction force F, there will be F here, P there, and there will be a force P minus F, similar to what we had in the problem 2, but in problem 2 the F was a prescribed value, but now F is not a prescribed value. Problem 2 F was given to us, now we do not know what F is and we have to find what that F that will satisfy this requirement that C cannot displace by more than a amount delta. Okay. So, now delta C would be, this is similar to what we had in the problem 2. So, delta C now would be PL by AE minus 2F L by AE, and this displacement cannot be more than delta, right. So, that is the displacement that you can have, delta C can be delta. Okay. So, you use this equation now to find what F is. F is delta AE by L P minus delta AE by L into 1 half. Okay. So, F is 1 half P into P minus delta AE by L. Okay. Now, let us understand what this means. F would be greater than 0 if delta is less than, or delta is if delta is less than PL by AE. Okay. F will be greater than 0 if delta is less than PL by AE. How do I get that? I get from the fact that P minus delta AE by L has to be greater than 0, which means P must be greater than delta AE by L. This implies delta has to be lesser than PL by AE. Okay. PL by AE. Okay. Else what happens? F becomes negative. Is a negative force possible here at C, which means is a tensile, can BC be in tension? BC cannot be in tension because there is no force applied at NC, and if the gap is there it can be only in compression, not in tension. So, if you solve this problem and get your force to be a tensile force rather than being a compressive force, in other words if F happens to be negative, wherein we assume the positive direction of F to be the compressive force, then what happens is you have to set that to 0. Okay. So, the solution is F BC is equal to two cases P minus delta AE by L into half if F is greater than 0 or delta is less than PL by AE, else it is 0 if F is less than 0 or delta is greater than PL by AE. Now, in problem 1 we saw that the expansion that C will have due to the applied load P is PL by AE, right. In problem 1 we found that delta B is PL by AE and that is equal to delta C, right. Delta C and delta B were PL by AE. So, the gap is more than PL by AE, then the C will have free expansion and there will not be any, when delta is greater than PL by AE, C will expand freely and there will not be any force, reaction force that comes about at C. Okay. That is what we are saying here. That is what we are saying when we say FBC is 0, that is what we are saying when we say FBC is 0. Okay. Similarly, FAB would be P minus F, so it will be P plus delta AE by L into 1 half if delta is less than PL by AE, and it will be P if delta is greater than PL by AE. Because F is 0, this is essentially P minus F, is what this is. So, P minus F will give me that. Okay. That comes from the observation that at AB P minus F is the axial force that this member AB sees, this P minus F. Okay.